Hey everybody, Greg here, and I just wanted to go over the position, velocity, and speed activity from class, and I wanted to do it slowly, deliberately, and giving you all the details you need so that you can really understand what's going on here. So let's just first set up the situation. So the situation was simply that we had a basketball that was thrown up and at an angle, like this. And after it's thrown, it just follows this trajectory. Trajectory just like this, right? Just from experience, you've seen a ball follow a parabola like that before, I'm sure. And the reason why there is 1, 2, 3, 4. Let's count these. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 basketballs in this picture is because this is a picture where over the course of it following this trajectory here, we're just taking pictures one every 1/25th of a second. So from the first picture here that's taken to the second one here, 1/25th of a second has gone by. And then between this picture being taken and the picture of the basketball being here, 1/25th of a second, this is seconds, is taken, and then, keep going like that, 1/25th of a second, through all of these. And so the amount of time for this entire picture is going to be 13 over 25 seconds. So why 13 and not 14? Because there are 14 basketballs. So like when we counted each of these basketballs, we counted 14. Well, the reason why it's 13 over 25 is because first consider if there were only 2 basketballs. So consider if there was only this first basketball, okay? And then the second basketball. Now there'd be 2 pictures, but there'd be 1/25th of a second, right? Just 1/25th of a second between those 2. If there were 3 basketballs in the picture, we only saw, this first one, the second one here, and then this third one here, then that would be 2. That'd be this and this, so 2/25ths of a second. So whenever you have a picture of this, it's the amount of time that goes by is going to be the number of images you see minus 1 times the time between pictures, right? The time between the pictures. And this is going to be like the time total. And so here our time, which we can call delta t, or we could call it time total, is going to be equal to 13 over 25 seconds, right? It's 14 minus 1. That's this n minus 1, 14 pictures minus 1. And then times are 1/25th of a second. That's the time between pictures. So that's how we got get that delta time, and that's what's going on in this picture. Okay, so now let's really get into what we're being asked here. So to understand the velocity of this basketball, we need to first understand the position. So the position vector we usually write as r with a little arrow over it to show that it's a vector. And for the position vector, that's just a vector from the origin to the object, okay? So if we draw the initial position vector, then that initial position vector is going to be from the origin right here, right there, to, let's say, the center of the basketball. Usually, if it's an extended object, try to find the center of mass and draw the vector. So the vector is going to be this arrow here, and we'll call that r, right? So it's a position vector. Call it r with a little vector over it. And then we'll put an I there because it's the initial one. And then we're also asked the final position vector of the ball. So the final position, just in red, is going to be this arrow here, and we will call that r sub f. Okay. So now we have our position vectors, and now we're asked to find the displacement vector. And so that's the difference between the final and the initial positions, right? So it's our final minus our initial. And so the way that we can do that is we can just look at the two positions of the initial and the final, and the displacement vector will just be an arrow that goes from the initial to the final. Let's do that in blue. Initial to the final there, like that. Okay, and then this is going to be our delta R vector, okay? That's what from the initial to the final is usually the delta R vector. And make sure you're always drawing the arrow from the initial, the thing that is being subtracted. That is where where the vector will start, and it'll end at the final position vector where the ball ends up later. So make sure that arrow is going to the right. Okay, so what we want to find is we want to find the average velocity of the ball. These angle brackets here mean average, and we have our velocity vector in there, so average velocity vector. And that's going to be defined as the displacement over the amount of time that went by. And so we already went over that there are 25 images per second. And so that's going to, and we calculated also that means that we had 13, sorry I drew over that a little bit, but you should be able to see there that the amount of time that went by, the delta t, is going to be equal to 13 over 25 seconds. So if we're trying to calculate the average velocity, we already have half the calculation done. We have the denominator, that delta t, done. So the next thing we need to figure out, though, is we need to figure out what is our displacement vector. So what is that as an ordered pair with an x component and a y component? And so if we look over here, okay, so we don't have any tick marks on our x-axis or y-axis. That is typically a good way of finding how much distance something has traveled, how big a vector is. But here, the only thing that we know is that the basketball has a diameter of 23 centimeters. So what we can do is we can say, okay, well, let's just look at how far this, our delta R vector, so let's see how far that went in the x direction. And we know that the basketball is 23 centimeters, so a distance like this is 23 centimeters. And so how many of those intervals make up our blue arrow here, our displacement vector? So let's just try to estimate. So this looks like about 23 centimeters, about the diameter of the basketball. This looks like another one. We're going to go all the way to the center of the final position vector. So okay, so this looks like 1, 2, 3, 4, 5 basketball diameters. And if we do a little calculation, 5 times 23 equals 115. We're working in centimeters here, so the x component of our position vector is 115 centimeters. And you can do the same thing where you estimate how far up, so basically how far from, say, this y height, like this, to, say, the center of the basketball right here. So we try to figure out what the distance is right here, and it looks like maybe around a third of the basketball's height, and so maybe around 8 centimeters, because the basketball is 23 centimeters in diameter, and so I'll say that this is 8 centimeters. Now all we have to do is combine these two in this equation here, since we have both our time and our displacement. And doing that, we can say that our average velocity is equal to 115,8 centimeters. It's okay to take the centimeters out of the parentheses. Divided by 13 over 25 seconds. And then if you work that out, that is equal to 225,15 centimeters per second. And so that is our average velocity vector. Okay, on to the next question, which is just asking what the average speed is. So the average speed is not a vector, it's a scalar, it's just a number, and it's the total distance traveled divided by the total time. So we can write average speed, there's no arrow over that vector sign, so it's the speed, is equal to total distance along the path traveled divided by the total time. And we know the denominator at least is the same thing because we're still talking about the same path that this basketball traveled, and before we found out that that was 13 over 25 seconds. So we can put that down here. And now the total distance traveled along the path, well, that would be this line here, how long this line is. And we already calculated that our vector for the displacement was 115, and if we look at the distance of that, it seems as if maybe that's about the same as this distance. Maybe that's the same as this distance. So that's 115 times 2, that would be 230. And maybe we're missing a little bit of distance here and also a little bit of distance for it curving. So I'm going to say 238 centimeters. And then if we simplify this, what we find is 457 centimeters per second. And that's our average speed. And then finally, we have the instantaneous velocity. And that's defined as the average velocity vector over a very short interval of time. And so what you can do is look at the distance between any two of these pictures. So these two basketballs are pretty far apart. Then when we get up close here, any two basketballs are pretty close together, and that means less distance, right? So the distance traveled between the basketballs in 1/25 of a second is this, whereas earlier, when the basketballs are further apart, say here, more distance was traveled in that same period of time, 1/25 of a second. So we know that, for example, this basketball's instantaneous velocity is going to be fairly big because more distance was traveled in that same period of time. And the instantaneous velocity of, say, this basketball right here will be fairly small. Right? This is the instantaneous velocity vector. And then it will get big again when we go over here, and then it'll be much bigger when the balls are even further apart over here. So I hope this was helpful for understanding position, speed, and velocity, and feel free to contact us with any questions that you have.